In this video, we're going to talk about change of variables in multiple integrals. How to express an integral in terms of x and y, in terms of a new variable, let's say u and v. Alright. Now, make sure you watch this video to the end, okay? Because we are going to talk about double and triple integrals in this particular video. I want to express this integral, the double integral of x minus y dx dy, over the region arrow, in terms of u and v, where x is this and y is this. Solution. X is equal to u into 1 plus v, which is u plus uv. Y is equal to u minus v. What we are going to do is to determine what we call the Jacobian or the Jacobian determinant. And the Jacobian determinant, which is the Jacobian of u and v, which is the partial derivative of x and y with respect to u and v, is the determinant of the partial derivative of x with respect to u, of x with respect to v, the partial derivative of y with respect to u, and of y with respect to v. Partial derivatives. What is the partial derivative of x with respect to u now? Come here. Let's differentiate this with respect to u. With respect to u, we'll take v as a constant. So if I differentiate u, I'll get 1. And if I differentiate uv with respect to u, where v is a constant, I'll get v. If I differentiate x with respect to u, which is the partial derivative now, u is a constant. Okay, so this will give me 0, the derivative. If I differentiate uv with respect to v, keeping u as a constant, that will be u. The partial derivative of y with respect to u, keeping v as a constant, if I keep this v as a constant, it means that the derivative is 0. Differentiate y with respect to u, we get 1. And if I differentiate y with respect to v, the partial derivative, it means that u is a constant. Differentiate minus v to get minus 1. And what would this be? This times this, that's, okay, minus into 1 plus v, minus this times this, as u. So this is simply minus 1 plus v plus u. So this is the Jacobian determinant of the transformation. Now, this integral is now equal to this. What is x? X is u. Okay, u plus uv. What is y? U minus v. So we have minus u minus v. Minus u minus v. And I'll multiply this by the absolute value of this, which is the Jacobian determinant. Minus 1 plus v plus u. Times, in place of dx dy, we write du dv. So the double integral over the region arrow, u minus u is 0. So I'm having uv minus v, and that's uv plus v. What this absolute value does is that it's going to change this minus to a plus. So we are having the absolute value of 1 plus v plus u du dv. So is either I leave my answer like this, or I can just write it without the absolute value. That is uv plus v into 1 plus v plus u du dv. So I have successfully written this integral in terms of x and y. In terms of two new variables now, u and v. This is it. Let's express the integral on the board, the double integral of x squared plus y squared dx dy in terms of u and v. Using the transformation equations, u equal to x plus y and v equal to x minus y. Looking at these transformation equations, u is the subject here and v is the subject. I need two equations where X and Y are the subject. U is X plus Y. V is X minus Y. Okay, see, I want to eliminate either X or Y. I can easily eliminate Y by adding both equations. So if I say U plus V, that's UV. Sorry, that's U plus V. X plus X, that's 2X. Equal to 2X. Y plus minus Y is 0. That is, X is equal to U plus V all over 2. From these same two equations, if I subtract, I added before. So U minus V is equal to X minus X, that's 0, plus Y minus Y. That's 2Y, we have U minus V. So Y is equal to U minus V all over 2. So let's determine the Jacobian determinant. The Jacobian of U and V, which is the partial derivative of X and Y with respect to U and V, is the determinant of partial X, partial U, partial Y, partial U, partial X, partial V, partial Y, partial V. Okay. The partial derivative of X with respect to U here. If I differentiate this with respect to U, it means that V is a constant and the derivative is 0. So differentiate U with respect to U to get 1. So we have 1 over 2. If I do partial X, partial V, I'll still get 1 over 2. If I do partial Y, partial U here, where V is a constant, I'll still get 1 over 2. But this will now be minus 1 over 2. You can verify it because differentiate minus V with respect to V is minus 1. So what would that give me? This times this as minus 1 over 4 minus this times this as 1 over 4. This will give me minus 2 over 4, which is minus 1 over 2. Okay, so this integral is now a double integral of what? X squared. X is U plus V over 2, so I will square it. What's Y squared? U minus V over 2, square it also. Then multiply this by the absolute value of minus 1 over 2. Okay, you get the point now. Then I'll say du dv, right? So this is it. Expand U plus V over 2 squared, we have U squared plus 2UV plus V squared all over 4. Okay, just watch. Expand this, you're also going to have U squared minus, it's not a minus, 2UV plus V squared all over 4. The modulus of minus 1 over 2 is positive 1 over 2. The minus will disappear, and du dv. So this is simple. I can do away with this bracket here. Yes, I can do away with the bracket. So I just add them up straight. Since they have the same denominators, 4, 4, I can just add their numerators. So that's what I want to do now. I'll just pick a single denominator, okay, which is 4, and add up everything. I hope you understand what I'm doing. They have the same denominator, so I can just add them up. U squared plus U squared is 2U squared. 2UV minus 2UV is out, that's 0. V squared plus V squared is 2V squared. All over 4. Then we have 1 over 2 outside. du dv. Alright, see something. 2 is common to these 2 outside, okay? So if I bring the 2 out, it can cancel this 1 under. Yes. Or if it cancels this 4, we will not be having 2 left yet. So whichever one it cancels, we are still on point. So we have the double integral of, let's say it cancels this one outside. If I factor 2 out from 2u squared and 2v, I'll now be having u squared plus v squared all over 4. The 2 that came out cancel this one under it, this 2. So this is the u dv. This is the integral. So this integral in terms of x and y have been transformed into this integral in terms of what? U and v, using the transformation equations. Let's see the next question. Keep watching. This time around, we're going to talk about triple integrals. Okay? All right, let's answer the third question. We have to express the triple integral of x plus y over z dx dy dz in terms of u, v, and w, using the transformation equations x equal to u plus v plus w, y equal to v squared w, and z equal to u minus w. We can easily do this. Let's go through it. This is a triple integral, and the new variables are u, v, and w in place of x, y, and z. Okay? So first of all, let us determine the Jacobian u, v, w, which is the partial derivative of x, y, and z with respect to u, v, and w. And that's the determinant of the 3 by 3 matrix. We have partial x, partial u, partial x, partial v, partial x, partial w, partial y, partial u, partial y, partial v, partial y, partial w. Then we have partial y, that's partial z now, partial u, partial z, partial v, partial z, partial w. So what's this? To get this, we differentiate x with respect to u, taking v and w as constant, that will be 1. To get this, differentiate x with respect to v, that will be 1 also, and this will also be 1. Here, we took u and w as constants, and their derivatives are 0. Here, we now took u and v as constant, and that's 0 derivative. So we have 1 if we differentiate w. Then, for this partial y, partial u, there is no u here, and that gives a derivative of 0. For partial y, partial v, we take w as a constant. That means we now differentiate v squared with respect to v, and that's 2v w. Then, differentiate y with respect to w. We take v squared as a constant, differentiate w to get 1. So 1 times v squared is v squared. Here, we differentiate y with z with respect to u, taking this as a constant, and that derivative is 0. So we have 1. Differentiate u to get 1. I hope you are following me. Here, differentiate z with respect to v. There is no v here, that's 0. Differentiate z with respect to w, taking u as a constant, and that will give us minus 1. So let's evaluate this 3 by 3 matrix, the determinant. Plus, minus, plus. Plus 1. Okay, let me write it down. I want to go straight. Close this column where 1 is, close this row. We have this, and this. So this times this is minus 2VW, minus this times this is 0. Then we'll take minus 1. Close this, close this. We have 0, v squared, 1, minus 1. 0 times minus 1 is 0. Then this times this, v squared. Then we'll take plus 1. Close this, close this. We have this, and this. 0 times 0 is 0. This times this, 2VW. So minus 2VW minus 0 is still minus 2VW. 0 minus v squared is minus v squared times minus 1. That will be plus v squared. 0 minus 2VW is minus 2VW. So we have v squared minus 2VW minus 2VW is actually minus 4VW. Let's keep this somewhere. V squared minus 4VW. That's the Jacobian determinant. We're going to make use of it. Now, watch. The triple integral will now be, what's x? X is u plus v plus w. What's y? V squared w. What's z? U minus w. Multiply this by the modulus of this, which is the Jacobian determinant. That is v squared minus 4vw dy. It should now be du dv dw. You get it? No longer the y, no longer the x, dy, dz. So this is the triple integral of, let's see, okay, there are no like terms there. U plus v plus w plus v squared w all over u minus w times this v squared minus 4vw du dv dw. So I can write this as u plus v plus w plus v squared w into v squared minus 4vw divided by u minus w and du dv dw. So this is the integral now. We've transformed this one in terms of x, y, and z into u, v, and w, and this is what we have. Evaluate the triple integral using the transformations. Okay, u equal to 2x minus y over 2, v equal to y over 2, and w equal to z over 3. First of all, let's make x, y, and z the subject of the formula. From here, y is equal to 2v if you cross multiply. From here, z is equal to 3w if you cross multiply. Let's see what happens here. If we cross multiply, 2u is 2x minus y, right? So making x the subject of the formula, 2u plus y is equal to 2x. Remember that y is what? 2v. So 2u plus 2v is 2x. Divide both sides by 2. It means that x is equal to u plus v. This is it for x, y, and z. So the Jacobian determinant is partial x, y, z. So partial x, partial u, v, w, which is determinant of partial x, partial u, partial x, partial v, partial x, partial w, partial y, partial u, partial y, partial v, partial y, partial w, partial z, partial u, partial z, partial v, partial z, partial w. Okay, I think this one will be easy. Let's see. The partial derivative of x with respect to u. From here, we are going to keep v as a constant. So differentiate u with respect to u, that's 1. Differentiate x with respect to v, that's the partial derivative, keeping u constant, we'll still get 1. Differentiate x with respect to w, keeping, okay, there is no w here in the first case, so that will give us 0, the derivative. Differentiate y with respect to u, there is no u, so we are writing 0. With respect to v, that's going to be 2. And with respect to w, there is no w here, so we should write 0. Okay, this will be with respect to u now, that will be 0 also. I hope you are following me. But with this one, there is no v, to still be 0. And the partial derivative of z with respect to w, that's 3. So let's evaluate this. The first one is a plus 1. Eliminate this column and this row. We have 2, 0, 0, 3. 2 times 3 is 6. 0 times 0 is 0. Then we have minus 1. Close up this column and this row. We have this, 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 and this. This times this is 0. This times this is 0. Everything here is out. Okay. Then the last one is plus 0. Of course, everything there will also be out. Close up this column and this row. We have this, 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 this. This times this 0. This times this 0 is also out. 6 minus 0 is 6. So the answer is 6. That's the determinant of this matrix. We are not only going to transform this function here, we're also going to transform the limit. This, the s comes first. Okay. It means that this one is for x. This first limit. The y comes second. This is for y. The z comes last. This is for z. So see how I'm going to do it now. Let me keep this somewhere. Let me keep it here. 6. The integral is now the triple integral. What's x? X is u plus v. What's z? 3w all over 3, right? Times the modulus of the 6, which is also 6. So I can remove the 6, the modulus rather, and just put a 6 at the side here. I'm not wrong. Then we now have du, dv, dw. It can be dw, dv, du. So insofar the limits are also in accordance. If I write du first, the first integral will be from u1 to u2. dv next from v1 to v2. dw last from w1 to w2. You get the point. So if I write w first, that's the w. This one will be from w1 to w2 and so on. Now, let's transform it completely. The limit, we will not put this limit here again. This is from x1 to x2. You know, we started with dx, so this is x1, x2. When x is y over 2, what's u? This is u1, and this is x1. So when x is y over 2, what is u? Remember we said x is equal to u plus v. So if I put this one for x, y over 2 is now equal to u plus v. But I don't want to write v. Remember we said y equal to 2v. So if you make our v the subject formula, we have v equal to y over 2. So I'm going to put y over 2 here. If y over 2 cross to the left, it becomes minus. So this minus, that's 0. U is equal to 0. This will cancel out 0. So when x is y over 2, u is 0. When x is y over 2 plus 1, we are also going to write y over 2 plus 1 in place of x. So we have y over 2 plus 1 equal to u plus what's v is still y over 2. This will cancel this. U is equal to 1. So this is it. So we have from u equal to 0 to u equal to 1. Now, the next one is what? dy. That is from y equal to 0 to y equal to 4. So, when y is equal to 0, what is v? You get the point now. Simple. If I put 0 here to get v, okay, I'm making use of the transformation equations now. 0 is equal to 2v. It means that v is 0. So when y is equal to 4, put 4 here. It means that v is equal to 2, right? Now, z. When z is equal to 0, what is w? Of course, if you have 0 here, this is 3w. W is equal to 0. And when z is equal to 3, what will be w now for the upper limit? Put 3 here. 3 equal to 3w. It means that w is equal to 1. So this is the integral we are going to evaluate. Simply give us 6u plus 6v plus 6w du, dv, dw. It's simple. We first of all take the integral with respect to u. If we differentiate this with respect to u, keeping v and w as constant, we'll be having 6u squared over 2 plus integrate this with respect to v. We now have, sorry, with respect to u, that's 6uv. The same thing here, 6uw. From 0 to 1, dv, dw. So let's plug in the limits now for u. If 1 enters for u, if 1 enters here to be used 1 squared, and that's 1. So 6 over 2 is 3. If 1 enters here, we'll be having 6v. If 1 enters here for u, that will be 6w. If I plug in 0, which is, I'm supposed to say minus, I'll now plug in 0, the lower limit. But if 0 enters, everything becomes 0. So there's no need for that. Let's now integrate this now with respect to v. This will be 3v. This will be 6v squared over 2. And this is 6vw. I just integrated this with respect to v. Then I have dw left. From 0 to 2. So it's simple. Plug in 2 for v. This will be 6. Okay, we'll be having 6 here. If I plug in 2 for v here, that will be 4, because v squared is 4. Okay, 6 times 4 is 24. Alright, 24 divided by 2 is 12. So here will be 12. 6 plus 12, that will be 18. So here will be 18. I hope you get what I'm doing. If I plug in 2 here, that will be 6. 6 times 2 times w, that's 12w. We have dw now. So we now integrate this one with respect to w now. And that will be 18w, okay? Mind you, I didn't plug in the lower limit, which is 0. Because if I had plugged in the lower limit, which is 0, I would still get this. 0 into this is 0, into this is 0, into this is 0. So is this significant? That's why I didn't bother to use the lower limit. So integrate this with respect to w, that's 18w, and this will be 12w squared over 2 from 0 to 1. So plug in the upper limit, that will be 18 times 1. 12 over 2 is 6. So plug in 1 here, that was 1. Okay. If I had plugged in the lower limit, I will still get 0, 0, 0. You get? So there's no need for the lower limit to be plugged in. 18 plus 6 is 24. That's the value of the integral. Okay, having applied these transformations. So this is how to do change of variables in multiple integrals by applying transformations and working with Jacobians. I hope you like the video. Keep supporting by subscribing to this channel, like the video, and share it with your friends and your classmates. I am the Complex Analyzer. I will see you in the next video. Keep watching.